this is John Black, Super Chemist. This is part 2 of time. Gamma is the time when you're moving over top of the time that you're standing still. Moving over still. Your new second over your old second. Or hypotenuse over vertical line. These are the 3 different formulas for time dilation for a rocket, for a rotating thing, that rotates around, and a planet. This right here is your gamma. Remember, gamma is the moving time over the standing still time. So here's moving over standing still, blah, 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 blah. But I want you to realize these M and this S, yeah, it's moving and standing still. I want you to think of it more of this way. M is for a machine. This guy is touching a gravity machine. A gravity machine is either a rocket, a rotating thing, or a planet. And the S stands for space, outer space. This guy is out in outer space, just floating there. He's inertial. He's not doing anything. Okay, man, it's not Earth, man. Earth is not inertial. It's an accelerated frame, for number 1. Number 2, it doesn't work out when you go through all 3 of these. When you're up here, it works out, sure. You can say this is the Earth, man, even though it's not right. You can say this is the Earth, man, here. But what about down here? Because it is not an inertial frame, it's an accelerated frame, it gets time dilated. So now here, TM, the moving guy, he's the Earth guy, and down here, this is the outer space man. See how it don't work out? It doesn't correlate. My way, you can go straight through here. This top guy touches the gravity machine, so does this one and this one. That's why they're on the top. That's why they're on the top of this fraction. Because their second is, remember, this is gamma. So the second is longer. If it was shorter, then we'd have a fraction. And we know gamma is always in 1 or more. Because it's a hypotenuse. So hypotenuses can only be 1 or more. It can't be less. That's how triangles work. See down here, if these were all in space, the T subscript S, then it all makes sense. They all mesh together, all 3 of these. Their way, it doesn't mesh together. Now, look at this first one. This is for the rocket. I want you to look at the formula. The formulas are exactly the same. And you might say, oh, this right here, this red part, that don't look the same to me. Okay, well, you got me there. But I want you to think of this, man. In this one with the rocket, velocity squared is linear velocity. You go this way, and you have a certain velocity going to the right there. And you're going in a line. See, we all know what that is. You're going 50 miles an hour down the road. That's your linear velocity. But let's say you're going down the road and there's a bend there. But you're still going 50 miles an hour. That would be somewhat relative to the tangential velocity when you're talking about rotating things. Let's say this thing is rotating and you're moving at 50 miles per hour going around this circle, just like my daughter's doing, 50 miles an hour. Meaning if this was a ball on a string and you let go of the ball, it would go off at a tangent, right? What speed would it go off on that tangent? The same speed it was going 50 miles an hour, right? If it's going 50 miles an hour around the circle, it's going to fly off at a tangent at 50 miles an hour, or somewhere around, very close to that. So, again, this is just tangential velocity is basically exactly the same thing as linear velocity. The only difference is you're going in a circle. The WR, right, in parentheses, and then you square it, that equals velocity squared, just like up here. This is velocity squared. This is velocity squared. WR squared equals velocity squared, but it's tangential velocity. But you can see they're the same exact thing. You're moving, 50 miles an hour, either straight or you're going 50 miles an hour in a circle. It's the same thing. These 2 formulas are exactly the same. And now look at this one. This is for the Earth. Everything's the same. 2gm divided by r. Look up here where it says escape velocity. It's the square root of 2gm over r. Down here, what is it? You want a square root of velocity. If you square this and you square this, this will become squared, obviously. But this over here will just become 2gm over r. And look down here. 2gm over r equals escape velocity squared. This right here can be replaced again with velocity squared. this is literally linear velocity. You can see all of these three equations can be replaced with this one single equation. See, and this 1 over this square root thing, that's your gamma. So remember, what's gamma? Gamma is hypotenuse over vertical line. And what's the hypotenuse? That's your new time. It's not the vertical one. It's the one that you stretched out in a diagonal. So that is your T sub M. Then your T sub S is what you would have had, this part right here, your vertical. So it's hypotenuse over vertical. They just want to make it look complicated. You can see gamma equals 1 over this, all this crap here. And that equals the Tm over Ts, just like up here. But they have the Tm as 1. Their ratio is 1 to something that's slower than 1. I don't do that. In mine, when I'm finding gamma, the top number is always bigger than the bottom number, and the bottom number is always number 1 because it's the smallest. But no, I want to compare it to this. This is 1 because it's the smallest. And then when you stretch it out, you're making it bigger. It's like, come on. See, this 1 in the numerators, right, on these, that's the hypotenuse. This square root thing, this is the vertical line. So this 1 represents your new time, or your dilated time. This represents your standing still time. So this is going to be smaller always than this. So when you have a time dilation of 2, you're going to have 1 over this will be 0.5, and that equals 2. See, no matter what my equations and their equations, you get the same exact answer once you simplify the fraction. But mine is more intuitive because 2 to 1 is more intuitive than 1 to 0.5. Or 3 to 1 is more intuitive than 1 to 0.33. Same with 9 to 1 is better than 1 to 0.111. You know exactly what's going on when I say 2 to 1, 3 to 1. You don't know what's going on when I say 1 to 0.111. I don't like that. I don't like all this weird math stuff here. Yeah, either way, you'll simplify the fraction and get the same answer. But I can show how both these equations, this equations right here, this is the Pythagorean's theorem. They just have it rearranged so it all looks funny, weird. This is Pythagorean's theorem. They just rearranged it. I want you to look at this next equation. This is the same exact all these equations down here, all of them, they're the same exact equation. Okay? Yeah, it's crazy. All right? This is just Pythagorean's theorem. C squared equals a squared plus b squared. I changed it to x and y because that's what we have. We have x and y components. And I kept the c, and then I just rearranged it so that the y square is on the other side all by itself. The y square is the vertical. Remember, y goes up and down. X goes this way, horizontal. So now you can do it this backwards way. And if someone wants me to do a video, I'll do a video explaining how they do this, and I'll rearrange. All they did was rearrange stuff, just like over here. That's all I did was rearrange stuff. That's all we do. That's what physics is about. You rearrange stuff and you replace them, like I did over here, so that it makes sense. All right. So, anyways, this is the same as this. Okay, exactly the same. And we'll go into it on the next video because we're going to figure out how to get gamma without doing this. First of all, you got 1 over something, so you got a fraction in there. Then you have multiplication and plus and minuses, and it's inside of a square root. This is crazy. I know this is not calculus, and this is simple actual math, but come on, man. Nobody remembers half the rules of this stuff. Why would they do that when you could just do this? You can see up here, if you go in a rocket ship at 11,200 meters per second, linear velocity, you will get a certain time dilation. If you are on a rotating thing, right, it's rotating, and it's rotating at 11,200 meters per second, meaning where you're at rotating, you are moving at 11,200 meters per second. That's your tangent velocity. It's the same thing though. If you're going 50 miles an hour in a car on a straight line, you're going 50 miles an hour. If you're going in a circle in a car going 50 miles an hour, you're still going 50 miles an hour. It's the same exact thing. It's just one is straight and one is curved. This one, Earth, the escape velocity on the surface of Earth is 11,200 meters per second. So again, you get the same exact time dilation. All these are the same exact time dilation. Why? Because their velocity is 11,200 meters per second. All three of them. Earth, we're going to explain that. You have to watch my gravity videos. But space-time is actually being accelerated down to Earth. Okay? And escape velocity is 11,200 meters per second. That's because on the surface of Earth, that is how fast space-time is moving. It's moving down to the center of the Earth. We know this. How do we know it? Because they draw little graphs like this. They draw graphs like this and they say this ball is falling. It stays on spatial coordinates D the entire time. Here's D. And then it falls to the ground. The ball is not accelerating. The space-time itself is accelerating. Because look, here's a spatial coordinates A, B, C, D. At 5, this is 1, 2, 3, 4 seconds. What about 5 seconds right here? Where did spatial coordinates A, B, C, D go? They're gone. They disappeared. They're inside the Earth. So it's not and that's why when the ball falls, it stays inertial, and then when you hit the ground, you become accelerated. And that's why an accelerometer on Earth says it's accelerating at 9.8 meters per second squared, and it says it's inertial when the accelerometer is in free fall. You're an accelerated frame of reference. And this is where I'm talking about why I'm updating my videos, because this is one of the misinformation things I was saying, was that at each altitude on the Earth, you have a different little g, right? On Earth, it's 9.8 meters per second squared. 2 radiuses away, or 3 radiuses from the center, it's like 1.1 meters per second squared, you know what I mean? The acceleration, little g. And so I was saying, oh, well, at Earth, then, you must be the velocity of the space-time must be 9.8 meters per second. And it, 2 radiuses or 3 radiuses from the center, it's like 1.1, because it matches up to the acceleration. No, that's wrong. Okay, that's wrong. The velocity matches, and what's funny, at each altitude, the little g stays the same. 1,000 meters above the Earth, little g stays little g forever. Okay, so that means that at each point in the altitude, right here, they all have a constant velocity, right? Even though the space-time is accelerating, because you are a little man, you can't. It's the acceleration. You don't even feel it. You know what I mean? It's basically constant velocity going through you, and that determines the time dilation. So this gets the same exact time dilation. Why? Not because you're moving through space-time at 11,200 meters per second squared. No, because space-time is moving through you at 11,200 meters per second. And that velocity determines the time dilation. So this spaceship here and on Earth will time dilate at the same exact rate. But since this ship is not accelerating, they will have different physics. If he's going at a constant velocity, he's going to be floating in a spaceship. This wouldn't be existing here, this fire at the end. You'd just be constantly, I shouldn't have, here, let me get rid of that. You're just floating, constant velocity. There is no acceleration, so the physics is different. The only way the physics can be the same is if you were accelerating at 9.8 meters per second squared, and it doesn't matter what your velocity is when it comes to that. Your physics will line up. But now the time dilation will be different from each frame. Does this break the equivalence principle? No, it doesn't. Because the equivalence principle is having people locked in rooms. You can't look at other frames and walk around and see stuff. If you're locked in a room in here and you're locked in a room here, this one's going at 9.8 meters per second squared, there's no physics that you could do that would let you know that you're time dilating differently. There's nothing. because you can't leave your room to see what he's doing, and he can't leave his room to see what you're doing. That's why it doesn't break the equivalence principle.